In this video, we will be talking about some of the basic operational amplifier parameters. The first parameter that we are going to cover is the input offset voltage of the amplifier. Ideally, the output of the amplifier should sit at mid-supply when the two input voltages have the same voltage or they're equal. However, a voltage will appear on the output under this condition. To prevent this from happening, a very small amount of voltage difference or offset is applied to the inputs of the amplifier, and this will set the output back to mid-supply. This amount of offset voltage is simply referred to as the input offset voltage. Input bias current. Again, this is a parameter that would ideally be zero. A positive input bias current refers to small current that's seen on the non-inverting input of the amplifier, and similarly, negative input bias current is the small amount of current that is seen on the inverting pin of the amplifier. Input bias current refers to the average of these two values. Simply put, input bias current is the average of the two input currents of the amplifier. Input offset current refers to the difference between the bias currents of the amplifier. Again, ideally the two currents should be equal to obtain a zero output voltage. However, there has to be a difference between two bias currents to set the output to zero. This difference is referred to as input offset current. Output impedance of an amplifier. Amplifiers should have very low output impedance, and usually it's assumed to be zero, and in this way, op-amps will behave like a voltage source, and it will be capable of driving a very wide range of loads. The next parameter we're going to talk about is slew rate. Slew rate refers to the maximum rate of change of the output of the amplifier per unit time. Usually it's expressed in volts per microsecond, and it tells you how fast your output of the op amp can follow its input. In the graph, you can see that the output signal is slewing. The blue signal is applied to the input of the amplifier, and the red signal or the output is trying to follow the input as fast as it can, but it slews at the rising edge and the falling edge. Next, we're going to be talking about noise of amplifiers. There are two major sources of noise, and we're going to touch up on them very lightly since noise is a very broad topic and covering noise in detail is outside the scope of this video. Internal noise of an amplifier, as the name carries it, is caused by internal components of the amplifier, bias current, and/or drift. Noise or unwanted portion of the signal is usually amplified along with a wanted portion of the signal. Noise is always gained in the non-inverting configuration, or the 1 plus the ratio RF over RG. There are certain ways that we minimize the amount of noise. One is by keeping the feedback resistors as low as we possibly can, and also we can use bypass capacitors in parallel with the feedback resistor at higher frequencies. Different electrical devices and components such as power supply or resistors can be the cause of external noise in amplifiers. We can use proper circuit construction to minimize the effects of external noise in our circuits. One way to achieve this is to use shielding around power supply or reducing the resistor values whenever it is possible. Common mode rejection is a feature of differential amplifiers. Op amps are amplifiers with differential input, So common mode rejection applies to operational amplifiers. Common mode signal is when both of the inputs of the amplifiers have the same voltage or they have a common voltage across them. Under this condition, the output of the amplifier should be zero or the amplifier should reject the signal and not amplify it. Common mode rejection ratio or CMRR is the ratio of differential gain of the amplifier to the common mode gain of the amplifier when there is no differential signal on the input. As the graphics in the current slide show, we see that the differential gain of the amplifier is in response to the differential input signal between the two inputs of the amplifier, and the common mode gain of the amplifier is the gain of the common mode signal. Common mode rejection ratio decreases with frequency. As we mentioned, common mode rejection ratio is the ability of an op amp to reject the common mode signal while it is still amplifying its differential signal. CMRR is usually expressed in dB, and the two equations that we have are two different ways to calculate common mode rejection ratio: 20 log of the ratio of differential gain to common mode gain and or 20 log of the ratio of the change in offset voltage to the change in the common mode voltage. Common mode voltage range of the signal. Common mode voltage range of the signal refers to the input voltage range for which the differential input pair is still within its linear operating region. The upper and lower limits are determined by different transistors and internal circuitry of the op amp, and we will go over them when we're talking about the internal circuitry of operational amplifiers. The next parameter we're going to be talking about is power supply rejection ratio. Power supply rejection ratio, or PSRR, is the ratio of differential gain to small gain of the power supply. Another way to look at it is the ratio of change of the power supply voltage to the change in offset error. When looking at a product's datasheet, you will notice that PSRR and CMRR are specified and guaranteed for DC conditions or for zero frequency. There might be additional supplemental AC curves for these parameters that show the behavior of PSRR and CMRR over frequency. Finally, we'll talk about the gain and phase margin of amplifiers. Gain margin of an amplifier is the gain of an amplifier at the point where there's already been a 180-degree phase shift, and if the gain at this point at 180-degree phase shift is more than unity, then the amplifier is going to be unstable. That's because once there's been a 180-degree phase shift, feedback is actually going to be positive. In terms of dB, that means negative gain is going to be stable at 180-degree phase shift. Phase margin is the difference between the phase when gain is unity or 0 dB and 180 degrees. If at 0 dB, the phase lag is greater than 180 degrees, the amplifier is unstable for the reasons that we just mentioned, because that would imply that the gain margin is positive. In this graphic, we can see that the phase margin and the gain margin of an amplifier, which is clearly stable. The gain margin has a negative value, and it is measured when there's been 180 degrees phase shift in the amplifier. The phase margin happens at 0 dB, and the phase lag is less than 180 degrees. The next two parameters we will talk about are actually datasheet limits that play important roles. The first one is absolute maximum ratings. As the term carries it, the maximum here refers to the maximum limits that an op-amp will actually be able to operate safely. If the op-amp is forced to operate under conditions that exceed the maximum ratings, there will be permanent damage to the internal circuitry of the op-amp. Absolute maximum ratings are usually mentioned in the data sheets. Next is operating ratings of the amplifier. These are conditions under which the amplifier is functional. However, specific performance guarantees do not apply to these conditions. An example could be an op-amp for which the guaranteed table specifications are when there is plus or minus 2.5 volts supply, but operating rating of the amplifier exceeds these values. In the final part of this video, we will go over op-amp internal circuitry. As mentioned before, please keep in mind that this is going to be a very simple and general amplifier, and there are many different variations to op-amp's internal circuitry and design. The graphic in this slide is just showing us the op-amp standard triangle. Instead of having three blocks to represent different stages of its internal circuitry, we have inserted the actual schematic. This should help in the process of understanding what each transistor is supposed to achieve. I think it is a good big picture view before we go into the details of each stage. This slide zooms in on the circuit schematic without showing the pins. The first part of the circuit that we're going to cover is the biasing circuit of the amplifier. The biasing provides the device with the current that it needs for driving all of the transistors in it. For this particular design, the biasing branch consists of Q12, R5, and Q11. The current through R5 is equal to VCC minus VEE minus the two diode drops divided by the value of R5. The current is seen at base of Q11. The next stage that we will talk about is the differential input stage of the amplifier. The current at the base of Q11 is mirrored to base of Q10. This current is then delivered to base of Q3 and Q4. The differential input stage consists of Q1 and Q2 in series with Q3 and Q4. Any differential signal across either one of these inputs will flow current through the input stage and then to Q8 and Q9. Q1 and Q2 are connected as emitter followers. This provides the high input impedance that input stage of this stage and eventually the operational amplifier needs. Q3 and Q4 provide DC level shifting. They also protect Q1 and Q2 from emitter-base junction breakdown. For NPN transistors, the emitter-base junction breakdown happens at about 7 volts of reverse bias. For PNP transistors, this breakdown happens at about 50 volts. If accidentally, the input pins have a large reverse voltage across, Q3 and Q4 actually protect Q1 and Q2 and prevent the op-amp from breaking down. Q5, Q6, Q7 along with the resistors R1, R2, and R3 form the load circuit on the input stage. This is a high impedance load, and this load converts the differential signal of the input transistors into a single-ended signal at Q6 collector. The single-ended signal is then delivered to the second stage of the amplifier, which is the gain stage. As we can see, signal from the collector at Q6 is fed into Q16's base. Q16 is connected as an emitter follower which gives the stage a very high input impedance. Since it minimizes the loading of the input stage of the amplifier, it prevents gain loss at this stage. Q17 is connected as a common emitter amplifier. The load of Q17 is the output of Q13B and reaches the PNP transistor and parallels with the input resistance of Q23, which is another PNP transistor. Output of the second stage of the amplifier is taken as collectors of Q17. One concept that is repeatedly used in op-amp circuits is active load. Active load is when a transistor current source is used as a load resistance. This way, you can achieve very high gains without the actual need for high resistors, and this helps us by saving chip area. Also, having a large value resistor would require a large supply voltage source. By using an active load, we no longer need to have the high supply voltage. An example of this active load is the load on collector of Q17. A compensation capacitor is used in this part of the circuit. It's a Miller compensation capacitor which provides frequency compensation for the amplifier. It is connected in the feedback path and it creates a dominant pole at about 5 Hz. This is going to shift the other poles of the amplifier further out. It also gives the op amp a fairly uniform 20 dB per decade drop. Finally, we will talk about the output stage of an op amp. Q14 or the source transistor and the Q20 or the sink transistor form the output complementary stage of the amplifier. Q14 and Q20 have larger areas compared to the other transistors so that they can provide larger currents with minimal temperature effect on the device. When the output of the amplifier is pulled positive, Q14 conducts more power and it pulls the output more towards the positive supply. The opposite happens when the output is pulled negative, meaning Q20 is going to conduct more and the output is actually pulled more towards the negative supply and it will move downward. This amplifier has short circuit protection. Like we talked about earlier, not all amplifiers have short circuit protection. Q15 provides short circuit protection for the source transistor or Q14, and Q21 provides short circuit protection for the sink transistor or Q20. Also, in this output stage, we see that Q18 and Q19 bias the output transistors in the linear region, and these two transistors are fed by Q13A, which is shown at the very top of the circuit. Q23 is connected as emitter follower. This minimizes the loading effect on the output of the second stage of the amplifier. The output stage that we have presented here is a Class AB output stage. As we've already mentioned, Q14 and Q20 have larger areas. That's because we want to be able to draw more current from them. The output of the amplifier has very low output impedance. During this video presentation, we went through some of the very basic configurations that you will see in the operational amplifiers, and that includes an inverting and non-inverting closed loop configuration. And we talked about the basic parameters of op amp, and we went over the internal circuitry of the LM741.